My name is Lou. I am one of the AI solutions engineers here at SuperAnnotate, and I will be joined today with Vahag, one of our machine learning engineers. So this webinar today will be recorded, just letting you know in case that's of interest to you. We will have some questions towards the end. So if you do come up with any questions, please drop them inside of our Q&A section and we'll be getting to them afterwards. Great. So we'll continue today here. Like I mentioned before, this is our third installation for our automated CV pipelines webinar series. And today we're going to be doing instance classification. We'll be talking about, what instance classification is. We'll dive in deeper into some actual use cases. And then at the end, we'll answer any questions regarding any of the topics we bring up today. Just to go into a general outline, I'm going to introduce SuperAnnotate for the folks that aren't too familiar with the company. We'll go and dive into why we're focusing on instance classification today. I'll demonstrate a little bit of how instance classification is performed on our platform. After that, we will be able to have a deeper dive into the actual process, in which case we'll also use a couple of demonstrations to kind of highlight the things that we're talking about today. And then finally, at the end, excuse me here. Just getting rid of these boxes on my presentation for Zoom. Okay. And yeah, so we'll finally finish off by showing how we would be able to automate this process of instance classification. Okay, so we'll start off with a very basic introduction to our company. Our company was founded by two brothers, Tigran and Vahan. Tigran studied biomedical imaging in his PhD, and Vahan was studying machine learning. They both kind of were in this field early on, and Vahan came up with a super pixel algorithm, which kind of allowed computer vision engineers and other people working in this space to really increase their efficiency and kind of produce data sets that were nicely and correctly labeled so that they can use for their machine learning research. So this kind of research took hold of the academic community. A lot of people were very interested in it. We can see here a couple of our advisors, especially people that were working in this space, really liked what they were seeing with how fast these type of models were capable of helping produce great data sets. And so we have a bunch of advisors on our board that kind of pushed us to kind of go into this direction and build a company and start providing services for other companies that were looking to also automate their processes. So we were founded in 2018. Up to date, we've raised about $20 million for our company and for our type of projects. And we have a global team of over 150 people working with us together from all around the world. Also very important to highlight that we're top ranked on G2, which is a platform that kind of focuses on these types of services. And we're very proud to say that we are actually very highly ranked on that platform. I'm going to go into a little bit of our actual offerings. So these three offerings here are kind of what we're based on. So the first part is the data ops platform, which is basically the software that's allowing us to upload data to it. We can then manage that data, distribute it accordingly to different annotators, have those annotations actually done on the platform. And so that's kind of the basic building block, if you will, for this kind of service here. That allows us to really leverage the current technology and tools to really provide high quality data sets in as a short amount of time as possible. Going over to the right hand side, we have a data ops services offering as well, in which we have a human workforce ready to provide the annotation jobs for you. So the workforce themselves will leverage the platform and the software. They're trained on it and they know the ins and outs of how to use the software. And so they can really speed up and improve any type of annotation job that they train for. And this kind of setup has a bunch of layers. So we'll have the annotators And then on top of that, we can have people doing quality assurance to kind of make sure that the annotations are going well. And then we can have another layer on top of that, which includes the project management aspect. So the project manager can decide, which kind of annotator should be focusing on which type of work, and how to scale up or down depending on the specific needs of that project. And finally, here at the bottom, we can see that we have also the MLOps services. So the MLOps services is kind of the glue that holds all of this together. It's provides custom script writing for any use case here. If we need to move data around from data ingestion up to the platform, if there needs to be any conversion scripts done after the data has been annotated in order to deliver the appropriate data format for you, that's also part of this service here. And then overall, just general consultation about best practices and how to avoid any pitfalls that might come up during these types of jobs. Great. So now that we've kind of talked a little bit about the company and our offerings, I'd like to also mention, what is the interest in instance classification? Why would a company be interested in this? So, many companies collect large amounts of data. It's very difficult to know exactly what might be present in that data. So instance classification kind of helps us to extract some relevant info from all that large amount of data. It helps us to categorize items. So if the company is working with specific products that they have and that they need to analyze, we can classify those items. We can get a count, let's say, if that's what's needed in that particular project. We can also distinguish between the different relative proportions of items in specific data sets. And so this allows us to draw insights from the raw data, such as images or videos, whatever it is that you're collecting, to be able to have an analysis and possibly do some type of prediction for whatever task it is that we're interested in. We'll cover a couple of actual specific use cases in a moment, but this is the general idea of why it would be interesting for a company to kind of go into instance classification. Moving further into this, there's a bunch of different types of instance classification. We'll start off with one of the simpler ones, which is when we're trying to classify between two different classes. That's called a binary classification problem. So in this example, we can see that there's a cat and a dog in an image. And so on the right-hand side, we can kind of see that represented for a human under the column pet. But if we want to represent this for a computer, we would kind of have to encode that information into something that the computer can actually read. In this case, we're making a vector out of the data, and the vector will contain a 1 in the position where that category falls into what we call a cat, and a 0 at the other spot, which in this case is a dog. And the opposite is true for when we're trying to classify or encode the word dog for our machine learning model. So like I mentioned, this is one of the more basic ones. We do have also the ability to have multi-class classification. In this case, you would have a bunch of classes, not just two. It could be 3 or more. And each one of those classes would be selected at the moment of classifying your instance. And now to also mention about instances. So an instance relates to a specific example of a particular object. So if we have an image with a cat inside of it, the cat right there, that would be one instance of the cat class. You can have multiple cats in an image, and each one of those cats would be another instance, in this case of a cat. And then we have one other type of classification problem, which is a multi-label classification. This is a little similar, but very different as well to multi-class classification. It's called multi-label classification. And in this type of problem, we will label an image with multiple labels, not just one. So that's the main difference between multi-class and multi-label classification. Our output would basically have just one label for multi-class, but we would select from many different classes. And then for multi-label, we would have more than one label in our output from multiple classes as well. Just to recap what we were just talking about here, we we can see that there are different types of classification problems. The binary case, we have 2 labels only. We choose one. In the multi-class problem, we have many labels. We also choose just one. And in the multi-label problem, we have many labels, but we're also allowed to choose different labels, more than one for that particular problem. Great. So here are just some examples where instance classification is applicable in industry, in real world problems. First, I'll talk about parking availability, which can be kind of tackled in this manner. We can see that we have a parking lot here, and we've outlined some boxes around some parking spots. Inside the parking spot, there can be a car or there could be no car. And so that's kind of where the binary classification would arise. And so depending on the type of class that's present in the bounding box, we can determine whether there's an available parking spot or not. We also see this done in traffic analysis. So for traffic analysis, we'll have some bounding boxes around vehicles of different types. And in this case, we can classify what type of vehicle is present in that bounding box. And it may help us count how many cars are passing by a specific time frame, or if there's a vehicle that shouldn't be in that specific lane, we can also signal those things out. And one last example that I can give for now are the fruit life cycles. So if your company is working in agriculture or something similar, you can take images of the vegetation that you're working with. We can start detecting those different instances. And once we've detected them, we can start classifying them depending on if they're ripe, if they have some type of disease, let's say, or if they are ready to be picked. All of those different things could be possible with the instance classification method we're talking about. Okay, so before we actually get to automating this process, I'd like to talk about how instance classification would work on SuperAnnotate in a manual way. Initially, classifying things manually, we would draw bounding boxes around those objects. Then we would have to right-click and select from a list of possible choices the appropriate class that object belongs to. So this is without having a pre-selection workflow. Everything is done manually. We also do support the ability to have a pre-selection option, in which case, before any annotations are done, we would select the class that we think are gonna fall under the annotations we're gonna be doing. In this case, I chose vehicle as my class, and then I just started drawing bounding boxes around the vehicles that I saw in the image. And so those kind of automatically get tagged with that class. There's another way to kind of semi-automate this process on our platform, and that's by setting up a workflow. So the workflow will allow you to set some predefined steps for annotating. So in this case, I've selected 3 steps. The first one is going to be a vehicle. The second one will also be a vehicle. And the third annotation that I do on the platform is going to be of a pedestrian. And so anytime I go into the editor and I start drawing bounding boxes, that will be kind of the order in which those annotations will be done for me. So that's kind of a semi-automated approach. It still kind of involves some manual setup in the beginning, and also you need to then follow specifically that workflow. It can't really be adjusted in an impromptu fashion. Great. So now I'll pass it over to Vahan, who's going to take a deeper dive into the classification.
All right, so let me start sharing my screen and tell me if something is wrong with the screen or if you cannot hear me. Let's start. All right, so like Lou already described, the instance classification is the act of assigning a class to a particular object in the image. And here in the GIF, you can see another example of that, of drawing a bounding box and assigning the class of a person to it. What we are trying to do is we're trying to take the human out of the loop a little bit, not entirely, because otherwise would solve every problem, to automate this process. And the benefits of the automation are basically we can do more annotations and makes the thing faster. And once again, to recap, you can manually assign the class, or you can set up a sequence of default classes and follow that workflow. However, we believe that it is possible to have a feature in our platform that would allow us to automatically classify instances in general, not in all cases. So why do we actually think that this is a good idea, a good machine learning task to sort of implement in our workflow? It's because classifying objects is it actually is a kind of one of the most solved problems. And I realized that my camera is off. Let me just, where is the, how do I do? Okay, start the video again. So, okay, why do we think that this is a good idea? This is a good idea because it's one of the most instance classification or image classification is one of the most researched topics in computer vision. And this is really what kicked off neural networks in computer vision. And this is the area where machine learning algorithms perform very, very well. As you can see from the graph that I have copied here, it says that we can actually reach top 1 accuracy of image classification on the ImageNet dataset, which is a dataset that consists of about 1,000 classes and about 2 million images. We can reach 90% accuracy with MBITH model. Well, of course, these models are very large and it would be infeasible to write them, to have them sort of as the backbone. However, the cool thing is that for a marginal loss of accuracy in top 1 category, and top 1 means we classified it and it's the correct class, we can get like 7% less accuracy, but with a lot smaller models. And so, but another question may arise that, okay, we can do this, but should we do this? And we believe that yes, it's a good idea, that there are several use cases that this might be applicable. One of the cases would be when we are classifying objects that require a strong knowledge of a given domain. Let's say medicine, that if we are annotating images of operation tables, and there are many different types of scalpels, many different organs even, or things that are very, very specific to the medical field that the average annotator that you might, the average annotator would not be able to differentiate. And the time of these medical professionals who actually can do it is very, it costs a lot of money, and coaching the annotators can take a long time, and you don't know if things would go well or no. So that's one of the cases where if we could automate it good, then we would significantly decrease the load of these more informed annotators, let's say. Another instance is the number of classes is too large, and it would take a long time to find the most fitting class. Like I said, the ImageNet dataset consists of 1,000 classes, and really finding this particular one that would fit the most is not an easy task. And it would take a long time, even if you know marginally, or if you have some idea what the class should be. And it's really not feasible to scroll over the whole classes and pick one. And of course, last but not least, in general, we have found that this actually does increase the speed of annotation. So if you are a company that works on per instance basis, this saves you some time. And by the end of this talk, I will tell you just how much, because we've done this and we've ran a few experiments. All right. So what does the so these are basically the steps that our suggested solution should follow. First of all, like, as you know, we will need some number of manually annotated images anyway, so that we can tune our open source, or not even open source, just our models to this new domain that we're trying to annotate. This number varies based on domain, but we have found that it is sometimes, surprisingly, it takes about 200 annotated images to be able to fine-tune one of the open source relatively state-of-the-art models to perform at about 78 to 85% accuracy on this new data set. But sometimes when you have a drastically different setting than the initial training data for the model was, for example, if this is some aerial imagery taken by a drone or at high altitudes, then it would take a bit more annotation. In general, it varies, but usually it's a doable number of images that you need to annotate. So once this threshold is reached, you should start to run the training. And of course, before running the training, you should choose a model, and the model that we chose for our own experiments is a vision transformer, and the training method that we decided to use is called DEIT, or DATE. It is developed by Facebook, or should I say actually Meta. So the model that we chose for this task consists of about 8 million parameters, and it's about like 300 megabytes, and one inference takes about half a second on a moderate powered GPU like K80s. All right, okay, so what do you actually then have to do? You will have to crop these instances that are already annotated using their bounding boxes and create a new data set from them, because we're trying to classify the instances, and for our purposes, the new image in the image classification task is the instance of it. You crop the already annotated images, the one that we talked about in step 1. This ends up generating a new data set of cropped images. You run the fine-tuning on these images, and you can then deploy your model to whatever platform you like and work with it however you like. Send basically the image, and it will to that endpoint, and it will return you the class, and you can put it in, and you can just classify it in the platform. Okay, I will actually. So what does this look like? It looks like this. If this is one of the images in the COCO dataset, you basically crop the instances of interest. There are more, but for brevity's sake, I cropped out a few. This is the new data set, and we run our training on these new cropped images. All right, actually, I have here a Jupyter notebook that will be a link to which we will give, that basically describes if you want to do this. If you want to do this on your own, if you want how this would proceed if you actually have images in our platform, but you want to test on your local machine. You don't want to do it in our platform. So why doesn't it let me click to the, okay. Again, the way you would set up your environment is, of course, you would have a CUDA-enabled GPU. I've installed Torch and Torch Vision, our SuperAnnotate SDK. The way you would set this up is you would have your test data and your train data. You would install TIM, which is a module that contains these open source models, basically vision transformers. Import the SDK, initialize it. If you are not familiar with our SDK and how it works, this is fine. This is just basic setting up. You don't really have to think about it that much. You export your folder. You export your project into your local folder. Basically, your directory should look something like this. After you've done the export, the class is JSON. tests and train 0, after which we suppose you should download the model. Once you download the base model, you would have it in some directory called a model. And that's about it from the setup side, and you will have to start creating your cropped data set. And one thing that to note here is that annotators would draw bounding boxes not necessarily in a pixel perfect way. That means that you may crop with different angles or with different occlusions. Basically add whatever augmentation you want to add to the data set that you think would improve performance of the model on actual real life data. So again, this is just some basic code that finds out if what the type of the instance is, crops it out, finds the minimum maximum coordinates, and crops it out. This deed converter is basically a helper class that allows you to convert annotations from the SuperAnnotate format to something that this repository would, basically code in the training repository provided that by meta research would allow. You run the conversion, which ends up, which creates your new folder structure. You have the crop test, you have the crop train, and the crop test 0 CSV and the crop train 0 CSV, which is basically the labels. The CSV files would contain the path to the file and the class numbered from 0. Okay, what we did was we actually forked the repository of the Facebook research team and made a few changes to it that you can run. It's geared toward using a specific kind of dataset. We use our deed converter and added this SA custom dataset format to basically make it work. That's not that hard code, but you can dive into it afterwards. But that's all it does. It basically allows you to train on a particular model. Then, don't worry about this code. This code is basically given to you in the repository. And then you just basically set up your arguments, run the training code. And after running this training code, you will reach we reached 76% on a data set, but I don't know what accuracy you would reach on your own data sets. Something around that, I would guess. Now you have the model, and all you need to do again was the step number 6, which was to run this model and get your predictions. You create an image. This is done actually using our SDK again. You download it, you run the prediction, and you upload it to the class. This is it. This is the strategy, how it would work and how it actually works behind the scenes in our platforms, as you will see in a moment in our live demo. Okay, let's go back to the presentation. So I said that we had an experiment, and the experiment looks like this. We have this date model, which is pre-trained on the ImageNet dataset. We created a subset of the MS Coco dataset, which is another very famous dataset. We picked 768 images for our train set. We picked 768 images for our test set. And using this methodology that I just described and showed you in the notebook, we reached a 78.2% top 1 accuracy, which is actually pretty good. That means 4 out of 5 classifications by the model is going to be correct, roughly speaking. And the classes, again, we took a subset of the Coco classes because it's 80 classes, which was 7. I tried to make this a long tail distribution to mimic the real world. There are far less cats and zebras than there are cars and people, basically. Using these classes and this methodology, we reach this accuracy. Now to the rest of the experiment. That was the project setup. This is the experiment setup. We will use the same test set on which we calculated the accuracy. We recruit two annotators, divide our test set into two equal parts. Basically, we will ask each annotator to annotate images, so half of the images manually, and then another half of the images using this tool. And we will compare their performance metrics. And the performance metrics are the time taken per bounding box, the accuracy percentage of the model, how many times they had to change, the class that was predicted by our model. Okay. However, there are again 3 different scenarios in which we can use this thing, in which you can use this approach, basically. The first one, and the most, I guess, the one that I've been building up to, is draw a bounding box. The tool classifies it on the fly. You just draw it, not necessarily a bounding box, as you will see in a moment. The tool just classifies it at exactly at that moment, maybe 1 second later, but that's it. Another use case is you would ask your annotators to draw empty unclassified bounding boxes, and then after some number of them are annotated, the platform will start classifying them in a batch way. This means this would work actually pretty well with the medical example that I gave. The annotators would find objects, and then the classifier would fix them up, and then the more trained physicians would fix the mistakes made by our model. And the third one is an extension of the first approach, and it will again classify it on the fly. But in this case, it might take some time, so the annotator would jump to drawing another bounding box. It would eventually be consistent. It will eventually annotate everything, reaching, basically running after the annotator and doing its job. And I will explain in a moment why this might be a good approach to do things. And yeah, right, so this is time for a live demo. And what could go wrong in a live demo? All right, so like I said, we had a class, these 762 test images. This is our test set, and let's try annotating things and see if our model actually works. First salient thing is this person. See, yep, classified it as a person on the fly. And one thing that I really want to emphasize again is that you don't have to draw bounding boxes. The bounding boxes are inferred. We can use the polygon tool to annotate this very pixelated car. Wait for it, and it gave the class car to it. Or if you want to have some fun, you can do it with a, what's this called? A cuboid. And again, classified it as a person. Let's do one other thing. Let's say an airplane. See if it works with airplanes as well as it works with cars and people, and it does. And again, most of the time, 4 out of 5 would be correct. And because I used various augmentations, I did not really have to draw the bounding box in a pixel accurate way so that the classification would be accurate. All right, that's for our live demo. Let's go back to the classes. Let's go back to the slides and see our results. Turn on the slideshow. So we had 2 annotators that ran over the images, as I said. The median time that it took them to annotate one instance was 3.7 and 3.9 seconds respectively, if they use this automated tool. And it took them 5.88 and 5.61 seconds, not the average, but the median time to annotate it. So you might think this is not that big of a jump, but we just had 7 classes and it was fairly simple. But in general, this would be a lot harder. And even this like 40% in performance increase, 30 to 40% performance increase is, I think, significant. And this last row is the percentage of reclassified instances. It means that the model failed for one reason or another. 28% for one annotator, 25% for the other, and these numbers differ because annotators annotate in a different fashion using bounding boxes that are not exactly tight, and the model is sensitive to variations. But in general, it actually aligns pretty well with our baseline of 76% or 78% accuracy. All right, so it's time to discuss our usage scenarios. The first one, what it has, what good things it has and what bad things it has. The ability to correct mistakes immediately, I believe, is a good thing. So you don't have to do a second round of of quality assurance on the images, but it requires a GPU instance to be run, and it potentially can be cost ineffective. Like, you would always have to have this instance somewhere on Amazon or on your end so that everybody can work. Speed of the prediction is essential, so small models have to be used, and small models would, well, be less accurate in general. The scenario 2 does not have this problem with cost, because you turn on the GPU, you classify, and you turn it off. It would be preferable in situations when domain knowledge is required, but it requires a two-step process to finish the annotation. You have to draw the bounding boxes, you have to wait for it to finish classifying, and you have to then do a quality assurance on those classifications. And the scenario 3 is the same as scenario 1. You can correct the mistakes immediately. It still requires a GPU instance to be run and can be cost ineffective, but the models can be a bit larger than in scenario 1 because you're not waiting for it to finish its prediction. You can classify another instance and it will eventually catch up with you. All right, and I think that's it on my end. We should probably jump to Q&A, if that's the agenda. So should I stop this check?
Yeah, I think we have a, let me see, I just can see one question, two questions here. One of them asks if we would be able to share this notebook with the spectators.
Yes, absolutely. We will, when we send you the link, we will, of the webinar, we will also send a link to a GitHub repo where the notebook is.
Awesome, great. We have another question from Shivam asking, can we use self-supervised learning to annotate the images?
Well, it's a difficult question. I guess what do you mean by self-supervised learning to annotate them? If you want to create some pre-annotations based on clustering your images and then using some form of KNN on it, yes, I guess in some domains on some tasks, but I don't really see how it relates to the talk we had. This was more about supervised version. But of course, if you want to use your own models and your own approaches, like one that I described with KNN and your clustering algorithm, you can, and you can work with our SDK to do it in our platform as well.
Great. All right, we have one more here. Says, are these methods limited to only instance classification on images, or the same method can be used for video, LiDAR, or other data types as well?
Well, okay, so in general, these things are not limited to image because everything needs to be a class. But again, we have to ask ourselves the questions, just because we can do something, should we do something? And the answer in cases of LiDAR is probably no, because most of the time that the annotation process takes is actually getting the point cloud, trying to look at it from different angles, and not the classification itself. The classification itself is a very marginal part of the task, which increasing its performance potentially at large costs, I don't think would be very feasible. Whereas in image classification, especially with multi-label and multi-class classification, this seems to be a very valid approach. On the same story with videos, basically most of the tasks that you're interested in videos is action detection or maybe object tracking, where again, most of the time is taken by trying to interpolate your polygon or your bounding box to see where it would move, as opposed to just giving a class. It would work, but I don't think it would be cost effective.
Gotcha. Okay. And kind of continuing a little bit on this, is there any plan to integrate point clouds for labeling?
You mean if we would have LiDAR in our tool? I guess, yes, it's on the roadmap. And if you mean if you could use this tool, this classification tool that I just demoed, then you can just ping our support or success teams and we can discuss if you actually want to do it or not.
Got it. Awesome. Thanks, Vahag. Okay, I think those are all the questions. If I missed any, can you help me out, Dave? I'm not sure. Let's see. Okay, we got one more coming in. It says, can we automate this to a point where we wouldn't need a CV engineer working on this? And can we have annotators leverage this automation using SuperAnnotate?
In SuperAnnotate, you will actually just click train a model and it would do it. So the involvement of the CV engineer would be minimal, but if the customer or you want to do something on your own, you do not trust our default models, or you just want to have better performing models that you believe that would work better on your data sets, then no. But in general, seeing as these models converge to a fairly high accuracy percentages, just clicking a number and trusting the AutoML algorithm seems to work in an efficient way. So the answer to that question is yes and no. If you're okay with the performance that we can achieve using sort of being blind to what the domain is and using our default algorithms to figure out best hyperparameters, then yes. But if you want to do something better, then no, you just have to have a CV engineer in there.
Of course. There's another question coming in here saying, may I note the accuracy of interpretation of objects with the images of poor quality?
Oh, well, what do you mean by poor quality? Like the Coco, the images on the Coco dataset that I showed were about their resolution was about 200 on 200. So I guess that is poor quality, and then you would get 76%. But if you mean on images way smaller than that, let's say something like 28 on 28 or 32 by 32, I really don't know. You would have to run experiments on your own. And I don't think it would make sense to use this large transformer model for that experiment. And if by poorer quality you mean images where the objects are blurred, well, the academic research shows that you can reach fairly high accuracies there as well, when some things are either blurred or obstructed or cropped out. That is also an active area of research. But yeah, about 70 to 80%. That would be the ballpark.
Great, awesome. So I think we're coming up on the end here of our webinar. I would like to thank everyone for joining us today. It was a great pleasure. and we will actually continue the series here. Next up is going to be video predictions. We'll be hosting that on May 12th. So make sure to come back if you're interested in learning about that as well.